Now let's look at a different type of exponential functions. Here let's try graphing y is equal to 1 times 1/2 to the x. Here my a is 1, my b is 1/2. Now if I multiply anything by 1, it doesn't change its value, so I can rewrite this as y is equal to 1/2 to the x. And if I want to graph this, I'm going to need several x values that I can plug in to find my y values. Again, I'm going to choose -3, -2, -1, 0, 1, 2, and 3. If I plug in -3 for x into this equation, I get y is equal to 1/2 to the -3rd power. This is the same as 2/1 to the 3rd power, or 2 to the 3rd power. 2 to the 3rd power is just 8. So if I plug in -3 for x, my y is equal to 8. If I plug in -2, I get y is equal to 1/2 to the -2 power. Again, this is the same as 2/1 squared. 2/1 squared is just 4. If I plug in -1, I get y is equal to 1/2 to the -1st power. That's the same as 2/1 to the 1st power. 2/1 to the 1st power is just 2. Next, I'm going to plug in 0. I get y is equal to 1/2 to the 0 power. Anything to the 0 power is just 1. Next, I plug in 1 for x. I get y is equal to 1/2 to the 1st power. Anything to the 1st power is itself, so this is equal to 1/2. Next, I plug in 2 for x. I get y is equal to 1/2 squared. 1/2 squared is 1/4. So when I plug in 2 for x, my y value is 1/4. And then lastly, I'm going to plug in 3, and I get y is equal to 1/2 to the 3rd power, and that's equal to 1/8. So let's plot these points. -3 and 8, -2 and 4, -1 and 2, 0, 1, 1 and 1/2, 2 and 1/4, and 3 and 1/8. Connect these with a smooth curve, and my graph will look something like this. Notice this is almost exactly the reverse of our previous graph. As my graph moves towards -infinity, my y value gets very, very large. But as my x value moves towards +infinity in the x direction, now my y value approaches 0. Notice when I plugged in 1 for x, I got 1/2. When I plugged in 2, I got 1/4. And when I plugged in 3, I got 1/8. So as I plug in larger and larger x values, my fraction gets smaller and smaller, or my denominator gets bigger and bigger. So as my x value gets larger and larger, my y value gets closer and closer to 0. So because my y value gets smaller and smaller as x gets larger, we call this an exponential decay. Notice that the only thing different here is my b value. Before, when my b was 2, I had an exponential growth problem. Now that my b is 1/2, I have an exponential decay problem. Well, whenever your b is greater than 1, you're going to have a growth. Whenever your b is a fraction, or between 0 and 1, you're going to have a decay. Now let's try applying an exponential decay function to a real-life problem. Here we're told that a basketball tournament invites 64 teams to compete in an elimination tournament. If every team plays in every round and half the teams are eliminated each round, how many teams will be left after 4 rounds? Well, if we're going to fit this to an exponential decay, that means it's going to be an exponential function, and we're going to put it in the form of y is equal to a times b to the x. Now I'm going to call y the number of teams left. That means our x is the only other thing that's changing, and that's the number of rounds. Now, before this tournament even starts, when our x is 0, then the number of teams we have is 64. If I plug this in, my y is 64, a times b, my x is 0, b to the 0 is just 1, so I have a times 1 is equal to 64, which means my a is 64. So just like when we had an exponential growth problem, our a is our y-intercept. It's our starting value. It's whatever y is when x is equal to 0. Now before, our b was equal to 1 plus r. It was 1 plus our rate of increase. Except this time, when we have a decay, that means our b has to be between 0 and 1. Our b has to be some fraction. Well, when you have an exponential decay, the only difference in our b between a growth and decay is that our b is not 1 plus r. Our b is 1 minus r. So what is our rate of decrease in this problem? Well, half of the teams are eliminated each round. Or you can think of 50% of the teams are removed. Well, if our r is 50%, then our b is equal to 1 minus, now 50% in decimal form is 0.50, so our b is just 0.5. Or you can think of that as 1/2. So we have our function. It's y is equal to 64 times 0.5 to the x. Now we need to figure out how many teams are left after 4 rounds. Or we want to find y when x is equal to 4. So we plug in 4 for x, and we get y is equal to 64 times 0.5 to the 4th power. Now 1/2 to the 4th power is 1/16. 1/16 times 64, that's equal to 4. So there will be 4 teams left over after 4 rounds. So that's how you can apply an exponential decay formula to a real-life problem. Now what if we were told that we had 2 points and these follow an exponential model? We wanted to know what that model was. Well, we've actually already done this, but we can try this again. If we know this follows an exponential model, that means this is going to be in the form of y is equal to a times b to the x. Now I can plug in these 2 points for x and y, and I'll get 2 equations that I can use to solve for a and b. If I plug in the first one, my y is 6, a times b to the x, or the 0 power. Now, b to the 0 is just 1. A times 1 is equal to 6, so my a is equal to 6. If I plug in my second point into y is equal to a times b to the x, my y is 162 times a times b to the 3rd power, because my x is 3. Now I can't do much with that equation, except I found out that my a was 6 in the first one, so I can plug that in there for a. I'll get 162 is equal to 6 times b cubed. Divide both sides by 6, and I'll get b cubed is equal to 27. Take the cubed root of both sides, You're going to find out b is equal to 3. So I have my b, I have my a. I can plug them into my standard form here, and my model will be y is equal to 6 times 3 to the x. And this completes the tutorial on exponential growth and decay.